Hello, everyone. My name is Logan Ransom, and today I will be outlining my project for the MECE 6333 Conduction and Radiation course. The project was titled The Effect of Temperature and Relative Humidity on Heat Transfer for Cooling Applications to the Human Body. So the goal of the project was to produce a product steeped in personal application and experience. This project was centered around three physical locations and climates that I have personally lived in. The next focus was on the mechanisms of heat transfer, primarily covered in the course, being conduction and radiation, while also covering convection and evaporative cooling aspects of heat transfer as well. Overall, the goal was to create a study on an engaging topic with practical applications to everyday life. So the project consisted of creating a mathematical model to numerically simulate human skin temperature over time in the form of an ordinary differential equation with four mechanisms of defined heat transfer. Assumptions and constant parameters were defined for the overall analysis, as well as individual studies. Four major analyses were conducted. These were a baseline of the respective climates, a humidity study, a temperature study, and a sweat-only mechanism study. Each of these studies will be discussed in a little further detail later on. Finally, conclusions were drawn based on the results. So to begin, the mathematical model driving the analysis had to be derived. This started with an energy balance using the first law of thermodynamics on the skin. Continuing, four modes of heat transfer were then expanded in the change in energy over time of the skin. And these were conductive heat transfer from the body's core to the skin, convective heat transfer based on the surrounding environment, radiative heat transfer based on the surrounding environment, and evaporative cooling, which is done through the sweating process. While not all the derivations are shown for brevity's sake in the presentation, the final ordinary differential equation for discrete numerical integration is seen here to solve for the skin temperature of the body over time. So a few assumptions were applied to all the studies conducted. The first being that core basal body temperature was approximately equal to the skin temperature. This was done under the assumption that skin temperature would be initially elevated beyond its normal temperature, that either being due to activity or being outside in elevated temperatures, and left to cool for an 1 hour period of integration of the mathematical model through the presented four modes of heat transfer. Another assumption is that there are no inefficiencies, no losses, or other forms of heat transfer occurring in the defined system outside of those that have been previously defined. A third assumption was that the given climates were studied in July, which is historically the hottest and most humid month in all three climates, those three climates being Houston, Texas, Knoxville, Tennessee, and Richmond, Virginia. And a sweat rate of 1 liter per hour was also assumed, as it falls within the bounds of reasonability for human sweat production. Further assumptions or parameters were study specific, and they'll be discussed a little bit further down respective to each of those studies. So here were a few of the constants required to solve the presented mathematical model in its full expanded form. I'm not going to go over each one in extreme detail, but each of these played a part in the calculation of heat transfer that occurred by each of the four modes presented. So they were all incorporated in either the conductive term, the convective term, the radiative term, or the evaporative term themselves in their fully expanded forms. So then we move to the baseline analysis, and the baseline analysis consisted of simulating the mathematical model with forward integration in 1 second time steps. All four mechanisms of heat transfer were actively working, and the average July high temperature and humidity for each respective climate was used to produce the results. And as you can see, the results are on the graph on the right, and they show the differentiation of skin temperature over time in respect to a 1 hour time frame in each of the three climates using their baseline July high temperatures and humidities in each of those three locations. So the humidity study consisted of simulating the mathematical model as well, forward integration in 1 second time steps. And all four mechanisms of heat transfer were actively working once again. But the difference in this study from the baseline was that the aim was to isolate humidity to see the effects of relative humidity on the cooling process. So therefore, the temperature was set to the average of all three climates, the average of those high temperatures in each in the month of July, while relative humidity was still varied with respect to each climate. So as you can see, the final results were much closer when keeping temperature constant and varying humidity. And so there's a second zoomed in picture that shows the slight difference in those kind of quasi steady state results after 1 hour. So the third study was the converse of the previous humidity study, and this was a temperature study. And that consisted once again of simulating the mathematical model with forward integration in 1 second time steps. All four mechanisms of heat transfer were actively working. And the difference in this from the baseline and the humidity study is that the aim was to isolate temperature to see the effects of temperature on the cooling process. So humidity was set to the average of all three climates for each of these cases, while just the temperature was still varied respective to each climate. So you can see the results here in the plot on the right. They're a little more distinct, so there was no need to zoom in to see those steady state results as you get closer to 1 hour. And the final study conducted was the sweat only study. And the sweat only study consisted of once again simulating the mathematical model with forward integration in 1 second time steps. The difference in this study from the baseline or the humidity or the temperature study was that the aim was to isolate heat transfer by evaporation only to see its effects on the cooling process. So that meant that all of the heat transfer terms in the ordinary differential equation were zeroed out manually in the code and set to zero, except for the evaporative term. That way we could see what the effects of just evaporation of sweat would be on the cooling mechanism. And air temperature and humidity were still varied according to the respective climates based on the parameters that were used. And as you can see, there is also a very, very marginal difference between the Knoxville, Tennessee and the Richmond, Virginia results in this case. So a secondary zoomed in picture was used to see the slight separation in those results. So overall, there are some more in-depth numerical results in my paper. I would encourage you to check them out if you're able to, or if you want to just ask me. But the results, the overarching results of each study conducted revealed a few findings. The first being that sweat-only heat transfer was the most effective in cooling down the skin temperature over 1 hour. However, this is an unrealistic oversimplification of the cooling process by sweat for the human body. In reality, you have all of these other mechanisms of heat transfer working. And so for accurate study of results, it's best to actually include all of those. It was seen that air temperature had a more pronounced effect than humidity did on the cooling of the skin temperature. And this is consistent with the equations. So when you look at the convective heat transfer value, it would change greater due to a larger difference in air temperature and skin temperature than the evaporative term would based on the varying of relative humidity. Overall, it was seen that Knoxville, Tennessee was the most conducive climate to skin temperature cooling when accounting for all standard processes of heat transfer. The only exception was when temperature was held constant, the only humidity was varied, then Houston, Texas was the most optimal climate for cooling applications, which was a very interesting find. Thank you all for watching my presentation, and I look forward to seeing everyone else's topics and their results.